Alright, these are examples 1 and 2 from the end of section 2-6. So end of section. This is the section on graphical integration. Alright, so in this first problem, it just says that a particle is moving along an x-axis, and this gives us the velocity versus time graph. The graph looks a little something like this. Pull out a ruler and like that. Okay. The first thing it asks is, what is the initial and final directions of travel? Alright, so what direction is it going to start out with? And we'll call this t is equal to 0. And then if there's some point out here, what is its final direction of travel? Is it moving to the left or is it moving to the right? So if we're on an x-axis like this, we're only moving in one direction. Let's call this positive and this minus, and this would refer to positive and this would refer to minus. What direction is it going initially? Well, the fact that its initial velocity is actually a negative number tells us that its initial velocity is going to the left, right? It is, if we call right positive, then it is moving to the left in the negative direction. What about its final direction of travel? Well, this is a positive number, and it is, so it's above the x-axis, or the t-axis in this case. That means it is moving to the right. A positive velocity would be moving to the right, and a negative velocity would be moving to the left. Now, don't be confused. We could still have a positive velocity and a negative acceleration, right? Just like if you threw something up and it came back down, it's got a positive velocity the whole time. Even though that velocity gets smaller and smaller, it always has the same magnitude of gravity, acceleration due to gravity pointing down. So this is just a velocity versus time graph that we're looking at. Part C says, does the particle stop momentarily? What does that mean? Does it stop? Like, if we want to write that in equation form, that literally means that the velocity at some time is equal to 0 meters per second. Well, if this is plus velocity and this is negative velocity, that makes this right in the middle, v is equal to 0. And we can see there is indeed some point, or it does come to a stop. And the graph in the book doesn't give us numbers. I drew it just like they did. But yes, it does stop. So it was going to the left if this is time, and time goes in the positive direction. The object was moving to the left, came to a stop, and then moved on to the right. So that confirms we had said that initially it was moving to the left, and finally it was moving to the right. Okay, I think there's one more part on this one. Is the acceleration positive or negative? Since this is a velocity versus time graph, I'm trying to give you some time to think about it. I'm not hesitating myself. Think about it for a second. Is the acceleration positive or negative? Well, we should know by now that the acceleration is literally equal to dv dt, which is the slope of the velocity versus time graph. Well, this is a positive slope right here, Yeah, it's constantly moving up and to the right, so therefore it is a positive slope, and it is a positive acceleration the whole time. Even though it changed directions, the acceleration was constant and positive. And how do you know it's constant? Because on a v versus t, if linear, then we can say the acceleration is constant. Okay, I think there's one more part. Is it constant or varying? Oh, I just said it. So part E is this acceleration constant? It is a constant acceleration. If we went back through the graphs, remember, constant acceleration was something that just went out like this. That would lead to something with a positive slope on our velocity versus time. And position versus time, we would get something parabolic. So know that constant acceleration has a linear slope on the velocity versus time and will be parabolic. I think I've said that about 8 times now. Alright, there's one more I wanted to look at. This was number 2. And I'm just going to roughly sketch it. Let me get a graph at least. It does go into the negative, so ta-da. Okay. It's a Chihuahua, and it's running erratically like they do. And they have the acceleration versus time graph. It starts out below the axis like this. It comes up to some point here. It levels out. It comes back to the axis. It levels out again. It jumps back that way, goes over, and then comes back. And it comes back to here. So acceleration versus time. Alright, these are just conceptual, so we don't need the numbers, and the numbers are not even given to us. We're just given intervals. This is interval A, this is interval B, this is interval C, this is interval D, and so on. It wants to know if the acceleration, which is just drawn, is of a Chihuahua as it chases a German Shepherd on an x-axis. Which of the time periods indicate that the Chihuahua moves at constant speed? Where on the graph is it moving at a constant speed? So, if you remember from one of our basic kinematic formulas, we have Vf is equal to initial velocity plus acceleration times time, and this is for constant acceleration only. Then we see this looks a whole lot like y is equal to mx plus b, right? Just swap those terms around. The acceleration is equal to the slope we've learned, and the initial velocity would be our y-intercept. So if v final needs to be equal to v initial, then we can't have accelerations. That's all I'm getting at right there. So if I look on the graph, right here is actually a negative acceleration. Anything up here, even if it's going up or down or leveling out, all of that is a positive acceleration. Anything right here, even though this is level and has a 0 slope, and even though this is change in direction, all of that is still a negative acceleration. What about this one spot, let me get a different color, it's so small. At that one spot, we're actually saying the acceleration is equal to 0. And in this case, it looks like the acceleration went from negative, it's a negative number, to a positive acceleration. I see one other spot, this interval right here. It is holding an acceleration equal to 0. Acceleration equals 0 is equal to constant speed or constant velocity. And we'll get that, we'll understand that pretty well when we get into Newton's laws, but you know Newton's first law. Something that's in motion stays in motion unless acted upon by an outside force, and same thing if it's at rest. Right? If it can be at rest or in motion, it's just not going to change velocity. And I'm going to keep writing this as often as it comes up. Newton's first law, I think you should try to remember as if, and you need all these words, if the summation of the forces is equal to 0, then the velocity vector is constant. So constant means 0 or any number, just not a function of time. It's not changing at all. Alright, see you next time.